Okay, so this is going to be a condensed review of everything relating to redox. I'm going to go through this at lightning speed and then probably go over a couple of more things in a little bit more detail tomorrow's class. But if you know the basics of this, you should be okay to get through any redox questions. So first of all, we have to talk about oxidation and reduction. Oxidation and reduction involve electron transfer. A reaction in which electrons are transferred from one atom to another is called an oxidation reduction reaction, which is then shortened to redox, the RED for reduction and the OX for oxidation. So we're going to be using the oxidation numbers that are found in the upper right-hand corner of each element on the periodic table. Oxidation numbers are usually written with the charge shown in front, such as +3, and then when we write it as an ionic charge, we usually do it afterwards, but you don't have to worry about that for purposes of this course. Just show the charge. As I said, oxidation is a loss of electrons from a substance, so electrons will be present on the product side because they're being released from the atom. So Leo says Ger. This is really important right here. Loss of electrons. Reduction is the gain of electrons by an atom of a substance. Therefore, if it's gaining it, then the electrons will be a reactant because they're added to the atom. And that's where we get the Ger from. Gain of electrons is reduction. So here's a couple of examples right here that you see. First, we've got Na. So I'm going to bring this down here. You're going to learn that anything by itself in the free state gets assigned a 0 oxidation state. When Na becomes an ion, it's a metal. So we know metals lose, it becomes Na+. So not only do we have to balance equations because of mass, we also have to balance them because of charge. So I have a 0 versus a +1. So if I add one electron to the right, that's a +1 and a -1, and it equals 0. Reduction is going to be the opposite. If I have Cl2, which is a diatomic gas, forming Cl-, because we know nonmetals like to gain electrons. Okay, but we have to balance our mass. There's 2 Cl, so I need 2 Cl there. And that each one has a -1 charge. 2 times -1 is a net -2. So I have to add 2 electrons to the left. So I have -2 and -2. As I said, oxidation reduction involves the transfer of electrons. What one loses, the other must gain. So electrons lost must equal electrons gained. That's really important. And I already said reduction is a gain of electrons, oxidation is a loss of electrons. Now we have two other words that come into play that are really important, and that's the oxidizing and the reducing agents. And the best thing that I can tell you to memorize this is it says an oxidizing agent is a substance that oxidizes another substance by accepting electrons, so we say the substance is reduced. Well, that's just like blah, 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 blah right now in your ear, I'm sure. So what I need you to remember is something very simple. If you take the upper level class, we'll get into this a little bit more, but for right now, just remember, whatever is oxidized is also the reducing agent. And whatever is reduced is also the oxidizing agent. So they're the opposite. Whatever's reduced is the oxidizing agent. Whatever's oxidized is the reducing agent. So let's look at this example I have here. I have K plus Br2 yielding KBr. And all I've done so far is balance the equation. So I have 2 Brs here, I had to put a 2 here, I have 2 Ks, I have 2 Ks. So one of the rules in assigning oxidation numbers is that anything by itself is assigned a 0. So this K is by itself, it's assigned a 0. Br2 is by itself because it's considered diatomic. So any diatomic molecule gets assigned a 0. Then when I get over here, just like naming compounds and writing compounds, I assign oxidation states. Br is -1 and K is +1. So let's look at what's happening. Let's take each one at a time. So I've got 2K, 0, going to 2K plus. So 2 times 1 is plus 2. So I have to add 2 electrons to the right because a plus 2 and a minus 2 equals the 0 on the left. This is oxidation. I lost electrons. How do I know I lost? Because I gave them up, and when I lose, I become more positive. Okay, just like we talked about when we form ions. And the other one is Br2, 0, going to, and it's 2 Br minus. So 2 times a negative 1 is a negative 2, so I need to add 2 electrons to the left side here. So negative 2 versus negative 2. So here the Br is reduced, and I know it sounds like an oxymoron, but it's reduced and it gained electrons. We know it gained because it's on the left side of the equation. So now here's the trick. We said that this is the oxidation that occurred, 2K0 going to 2K plus. But this is also known as the reducing agent. The 2K is the reducing agent. Here, Br was reduced. This is known as the oxidizing agent. So it's the opposite. All right, here's another one. This is the one I just did. Here's your oxidation. This is your reducing agent. Here is what's reduced, and this is your oxidizing agent. We have another one down here. We have N2, which is 0, and then here H is plus 1, and oxygen is negative, and N is negative 3. So we have N going from 0 to negative 3. That's reduced, so this is the oxidizing agent. And H went from 0 to plus 1. That was oxidized, so this is the reducing agent. All right, let's talk about some rules. These are a lot of rules. I'm going to go through them very quickly. As I already told you, elements in the free state, okay, get assigned to 0. Elements by themselves get assigned to 0, and that includes Brinkelhoff. The oxidation number from monatomic ion, the charge on the ion, for example, Ca is a plus 2, that's the charge. Okay, so any group 1 or group 2 element, the oxidation state is going to be, this is an ion, sorry. So the charge is given by the ion. The group 1, group 2 elements tell you their charge right in the upper right-hand corner. Normally, if I have 2 elements, the more negative one would be the oxidation state with a negative. The one that has the higher electronegativity is going to be the more one that's going to have the negative oxidation number, and that means that the SI would be plus 4 in this case. Fluorine is the most electronegative element, so therefore it is always -1 when it's bonded to any other element. Now there are some exceptions. Okay, we know that oxygen is usually -2. But because it combines with fluorine, and fluorine's the most electronegative element, fluorine is -1. -1 times 2 is -2. So here, oxygen assumes a +2 oxidation state. Only when it combines with oxygen. This is an exception to the rule. Another exception to the rule is peroxides. Peroxides have the general formula of X2O2. They look like that. Here's your hydrogen peroxide, H2O2. So here, the oxygen is going to be -1. Why? Because hydrogen is +1. +1 times 2 is +2. We know that this has to be -2 to be equal to 0. So 2 divided by 2, this is -1. So anytime we have a peroxide, and it takes this form right here, X2O2, O equals a -1. There's only two peroxides, H2O2, and the other one that they might show you is Na2O2, sodium peroxide. The last exception to the rule is when hydrogen combines with a metal to form a metal hydride, so LiH. Normally we know hydrogen is +1, but metals are very, very reactive, so metals are going to assume their +1 oxidation state, which means hydrogen is -1. Another example is MgH2. Mg is +2, and therefore this has to be -1. -1 times 2 is -2, -2 and +2 is 0. So anytime I have a metal hydride, hydrogen is going to be -1. You have to remember that the sum of the oxidation numbers are always going to be equal to 0. And if I have a polyatomic ion like SO4 2-, instead of it equaling 0, it's going to equal -2. So if oxygen is -2, that gives me a -8. What plus a -8 gives me a -2? So sulfur had to be +6 here, because that's the charge on the ion, so we equal the charge. Let's do a couple of these in practice. So Cu's by itself, it's 0, F2 is 0. This has got a charge, so it's simply the charge, which is +1. Now here we have to assign to each individual one. Since this is an ion, remember it's going to equal -2. Oxygen is -2. There's 3 of them. That gives me a net -6. -6 and what is a -2? That would have to be +4. So your carbon is +4. All right. Cl is -1. -1 times 4 is -4. So carbon had to be +4. Oxygen is -2 times 2 is -4. So sulfur had to be +4. I'm not showing you the math underneath. -2 times 2 is -2 times 2 is -4. Therefore, sulfur had to be +4 because the whole thing has to be equal to 0. Oxygen is -2 times 5 is -10. Whole thing has to be equal to 0, so this has to be +10. +10 divided by 2 is +5, so the P is +5. Here's our exception to the rule, Na2X2. So Na is +1 times 2 is +2, so this has to be equal to -2. -2 divided by 2 is -1. There's our peroxide. Oxygen's -1. Oxygen is -2 times 3 is -6. This has to equal 0. This has to be +6. +6 divided by 2 is +3. Here oxygen is -2. That gives me -6. Hydrogen's +1. Therefore, doing the math, nitrogen had to be +5. Oxygen is -2 times 4 is -8. Mg is +2. So for this to equal 0, sulfur had to be +6. Remember, I am only interested in these numbers up top. Okay? I'm only interested in these numbers up top. Alright? Just the ones up top. Bottom down here is showing you the math. I'm not interested in the math. I'm showing you that that's how you can do it and figure it out. Alright. I'm going to skip the one on the bottom there. It's getting kind of tight. I'll do this one up here. -2 times 4 is -8. K is +1. So therefore this had to be +7. CH4. H is +1. That gives me +4. This is going to be -4. And I'll do 13 down here. 13's a little bit crazy. I can show you a crazy one though. Alright. 2 times 4 is 8 for the oxygen. Oxygen's a -2. That gives me a -16. Remember, the whole thing has to equal 0. Then I have 2. Then I know that this came from up here. So 2 times 3 is +6. So that means that P has to be +10. And there's 2 P's, so each one is +5. You won't get one like this on the reagents. You'll get some of these easier ones in the second column and the third column. Half reactions. When something gains electrons and loses electrons, therefore redox, we use half reactions to show the oxidation and reduction. So if I have this equation, I'm going to write it down here. 2Fe plus 3Cl2 yields 3FeCl3. The first thing I want to do is assign oxidation numbers. Fe is by itself, it gets a 0. Cl2 is by itself, it's Brinkelhoff, it gets a 0. Chlorine is -1. I always use the top one on chlorine, and my halogens times a -1 is a -3. In order for this to equal 0, the iron had to be +3. So let's inspect what's going on. Fe is going from 0 to +3. So that's being reduced. It's becoming more positive. So I have Fe0 going to Fe +3, and I'm going to add 3 electrons to this side. That's my oxidation number. This is also my oxidation reaction. This is also my reducing agent. And in the other one, I have Cl2 going to 2Cl minus. So that's a -2, so this is going to be +2 electrons right here. So this is my reduction. It gained electrons, became more negative, and this is also my oxidizing agent. So let's do a couple of these. We have 0, 0, +1, -1. So I have Na0 going to Na +1, and that's 1 electron. I also have Cl2 going to 2Cl minus, which is a -2, so 2 electrons. Now, if I wanted to balance this half reaction, because I just pulled things out singly, I have to get my electrons to balance out. So I would multiply this whole equation by 2. Then I'd have 2Na, 2 electrons, and then my electrons would cancel out. Okay. So here I have Al is 0, it's by itself. Cr is 0, it's by itself. Oxygen's -2 times 3 is -6. This has to be +6. There's 2 of them, so 6 divided by 2 is +3. Over here I have oxygen -2, same thing, times 3 is -6. This has to be +6. There's 2 of them. This one's +3. So what do we have going on? We have Cr going from +3 to Cr0 here. So I have to balance this +3, so I'm going to add 3 electrons to this side. So this is my reduction. And then I have oxygen staying the same, so I don't have to worry about oxygen, it's just a spectator. And I have aluminum going from aluminum 0 to aluminum +3. I have to balance that +3 with 3 electrons, and that's my oxidation half reaction. Here I've got charges, so this is going to be +3 -1, this is 0, and this is 0. So I've got Cr +3 going to Cr0, so I have to add 3 electrons here. And then on the other side of this, I've got Cl minus going to Cl2. Notice my mass is not balanced. I have to add a 2 in front of this. 2 times -1 is a -2, so I'm going to add 2 electrons to the right, so I have -2 and -2. Now here my electrons aren't balanced, so if I really wanted to balance this half reaction, what I would do is multiply this whole thing by 2 and this whole thing by 3. And let's see what I get. I get 2Cr plus 3 plus 6 electrons yields 2Cr0. And down here I get 6Cl minus plus 3Cl2 plus 6 electrons. So now my electrons cancel out, and my final net reaction would be 2Cr plus 3 plus 6Cl minus yields 3Cl2 and 2Cr0. Alright, remember table J is your friend. It tells you what's going to be oxidized and what's going to be reduced. Most reactive is oxidized, least is reduced. So you just use where they are, RB and BA. So here's RB up here and BA here. So RB is oxidized, BA is reduced. Ca and Mn, Ca is here, Mn is here. So oxidized, reduced. Zn and K, Zn is here, and K is up here. So K is oxidized, Zn is reduced. Fe and H, H is right here, Fe is above it, so Fe is oxidized, and H is reduced. Cr and Pb, here's Cr, and it's above Pb, so oxidized, reduced. And Cu and Al, Al is here, Cu is down here, so Al is oxidized, Cu is reduced. Alright, we're going to talk about two types of cells. This is called a voltaic cell diagram. How do you know it's a voltaic cell? Because it has a salt bridge. You have to know a couple of things. First of all, salt bridge is flow of ions. Do not tell me electrons. Electrons flow through the wire. So electrons flow through the wire. You have two half cells. Oxidation is occurring in one and reduction in the other. So there's another saying now, and it's called red cat anox. And what that means is reduction at the cathode and anode is oxidation. So when you look at a cell like this, there's a couple of things. Sometimes it might be labeled anode and cathode. Sometimes there's a reaction down below, so you can figure out what's being oxidized, what's being reduced. And if all else fails, as in this case, you have to go to table J. So if we go to table J, we see that Mg is above Cu. So Mg is going to be oxidized, Cu is going to be reduced. So we know red cat anox, right? So we know that reduction occurs at the cathode. So this is your cathode over here, and this is your anode. And electrons flow, right, through the wire, and they flow from anode to cathode. And you can remember this because A comes before C in the alphabet. So anode to cathode. So as oxidation occurs, Mg, so this is our oxidation, Mg is going to go from Mg0 to Mg2+, which is why you see Mg2+ ions in solution plus 2 electrons. And the electrons are flowing through the wire to the copper electrode. And the electrons are going to all line up on this copper electrode. Okay? So what's happening then is you have Cu2+ ions in solution, and they're going to be like, oh, lucky me, electrons, electrons, let me grab 2 electrons and become Cu solid. So as this reaction proceeds, this electrode is going to eventually get smaller because it's losing electrons, it's losing mass. And this one is eventually going to get bigger because it's gaining electrons and forming copper solid, therefore it's gaining mass. All right, electrolysis. So this is an electrolytic cell. Let me back up one thing. I have to remember to tell you that the cathode is positive and the anode is negative here. In an electrolytic cell, notice there's only one cell and you have two electrodes. It involves a battery because this is a reaction that will not happen by itself. So you have to drive the reaction to happen, so you need a battery source. So the difference is that here the cathode is always negative and the anode is positive, which is opposite. I tell kids electrolytic ends in C, so that means cathode, and it starts with electro, which is like electron, so the cathode is negative. Therefore the anode is positive, and then you just have to remember that the electrochemical cell or voltaic cell is the opposite. So a lot of times what we are doing here is also electroplating. So we want to take an object like a ring and we want to put silver on it. Okay? What you have to remember is that the object to be electroplated, so if I have a ring here, is going to be on this electrode. And what's going to happen is the silver, which is the anode, right? We know that the anode is going to be oxidized. So a half reaction here would be Ag going to Ag plus. You see the ions in solution plus one electron. That's your oxidation half reaction. And this is going to get smaller with time. All the electrons are going to come up here, go through the wire, and they're going to plate all over this electrode and this ring. Then what's going to happen is the silver ions are going to go, oh look, electrons, Ag plus one electron, and form silver metal. And that silver metal is going to form on top of the ring. So to wrap this up, an electrochemical cell can either be voltaic or electrolytic. In an electrochemical cell, oxidation always occurs at the anode, reduction at the cathode. But voltaic cells are spontaneous, and they convert chemical energy into electrical energy, where electrolytic requires the outside power source, like the battery that you just saw, to produce chemical energy. And it's known as electrolysis. So I want to compare and contrast. So in both of these, right, we have red cat anox. For both cells, reduction occurs at the cathode, anode is oxidation. We also have Leo says Ger. Loss of electrons is oxidation, gain of electrons is reduction. Electrons also always flow from A to C, anode to cathode. And electrons lost must equal electrons gained for both of these. In a voltaic cell, it is spontaneous, which means it happens by itself. It converts chemical energy into electrical energy. The anode is negative and the cathode is positive. It has a salt bridge which allows the flow of ions. In an electrolytic cell, it is non-spontaneous. It takes electrical energy and converts it to chemical. That's why you have the battery. So we need a power source. And the anode is positive and the cathode is negative. And if electroplating is taking place, the object to be plated is always at the cathode. So the ring, the fork, and I think that's it. All right, that was redox and lightning speed. I hope it helped a little bit.